What is up, guys? Now, what we're gonna be doing is I'm gonna be teaching you guys a little lesson on gravity. So, I know you guys think you know everything about gravity, but you probably do for the most part. But we're just gonna go through some problems using gravity. And really, what it is this is just gonna be kinematics again, but it's using um, gravity. So instead of like x and y axis, it's more x axis, it's more y axis, right? So up and down. Um, and whenever something is falling, so as long as you're not throwing something, if it's just falling, then the acceleration is here. Let's write it down. So gravity, which is the acceleration of just anything falling towards the earth, is negative 9.8 meters a second squared. All right, so that's gravity right there. So now, a koala initially at rest, munching up on some eucalyptus, falls asleep, and then falls out of a tree 3 meters above the ground, right? So now we got a little cutesy ass tree right here. So now we got a little cutesy tree right here, and we have a koala. And this guy fell out of the tree, and he's fallen. And he falls all the way to the ground, which this distance is 3 meters, okay? So we're going to calculate the time it takes for the koala to reach the ground. Now, how do we do that? So this 3 is equal to a change in y. So I know nowhere here says change in y, but you see change in x is literally just the change in displacement. And this 3 meters is the change in displacement, just, on the vertical axis, which doesn't make a difference. So whenever we work with vertical stuff, then all our terms need to be vertical. So for example, we're doing change in y. So our acceleration needs to be on the vertical axis, on the y-axis, because there's no acceleration or movement going x, and there's no displacement on x. So everything is going to be in terms of y. So let's see. Calculate the time it takes for the koala to reach the ground. Well, we do not know time, but it's initially at rest, which means that our initial velocity is 0 meters a second. So now that we have all this information, I'm going to move this change in y is equal to 3 over here. So now what do we need to do? We need to find something that doesn't use v of f. So we don't know what final velocity is, so we're going to use that exact same equation, except we're going to put it in terms of y. So change in y is equal to vi times t plus 1/2 at squared. So change in y is equal to 3, which is equal to 0 times time. 0 times anything is just 0, plus 1/2 negative 9.8, and we don't know t, so it's t squared. Now, if we really want to get technical about it, this 3 is actually a negative, and the reason why is because this is the initial point and this is the final point. So this is at 0 and this is at 3, right? And change in literally anything is equal to the final minus initial of whatever, right? So if it was change in velocity, then it's going to be final minus initial first. Okay, it's always final minus initial, so it's 0 minus 3, which is equal to negative 3. And that is why it's negative. But oftentimes, I think when I was doing physics through school, I wasn't even really paying attention much to that kind of stuff. And honestly, what I would do is instead of like the -3 and -9.8, I would just say that this is 3 is equal to 0. So just 1/2, and then I would just make this 9.8 t squared, and I would just disregard the direction, and I would just get the answer right. And then if I needed to state the direction, I would just state the direction afterward. But if you want to get really technical about it, this is actually the correct way of doing it and writing the equation. So let's use that form then, right? So and always box in your answer. So I boxed that, but that's not the answer. So but you always want to box your answers, because what's going to happen is you're going to write down a whole bunch of work, and then you want to make it really easy for your teacher to find the actual answer. So you box it, you circle it, whatever. Now, so this is just going to be -3 is equal to 1/2 times -9.8, which is going to be about -4.9 t squared. Now all we have to do is divide by -4.9 divided by -4.9. T squared is equal to 3 over 4.9, which is going to be 0.612. Take the square root, and here, let's just go over here. T is equal to 0.782 seconds. Now, that's how long it takes for the koala to reach the ground. So basically, how long it takes for the koala to fall. To check your answers, you guys can see if this stuff makes sense. Does it make sense? If you're 3 meters above the ground, if you were basically to jump out of a tree, how long would it take? Probably less than 1 second. So this seems accurate. I feel like this is an accurate time. If you were to get 1,000 seconds, you might think you did all the math right, but use your brain. It's not. It's from 3 meters, you're not taking 1,000 seconds. I remember my friend, we were taking a quiz. I turned in my quiz. I got a reasonable answer, and it was like, what is the size of this like bug or something? And so I got a small answer, and so after I turn in the quiz, I come back, I see my friend still working it. I peep to see if he got the same answer as me, and my guy was in the millions for like a little like a centipede or something. You can't turn stuff like that in. You can't just think, well, this is where my math led me, so that must be the right answer. It's not. It doesn't make sense. Physics is always going to make sense. Especially physics 1 is really easy. It's stuff like this where you can think about it in real life and you can get answers right. So that was just a little tangent that I went on, but let's go on to the next example. Now, this is a continuation of the first problem we just did, and basically what we're trying to find now is what is the velocity right before the koala hits the ground. So when it hits the ground, then the final velocity, you would think, is 0. It's initially at rest, and then at the end, it's also at rest because it touches the ground. And that just messes up your math. So final velocity, whenever something is like initially at rest like this, final velocity corresponds to right before it hits the ground, because an object is accelerating at the speed of 9.8 meters a second squared if it's just falling. Now, if you're to throw it, it's even more than that. So it's getting faster over time, which means that the velocity is increasing. So the acceleration is constant, but because it's greater than 1, the velocity is increasing over time. So we want to know what the greatest velocity it reaches right before it hits the ground. So that's what final velocity is. final velocity is not when it hits the ground, it's right before it hits the ground. So, I know that might be like, whoa, how am I supposed to do the math for that? You don't really got to think very deep about it. You just do kinematics. It's truly simple. So what we're going to do is we're going to try not to use time yet, okay? And we're just going to find acceleration. So we're going to find something with no time. This. So it's VF squared is equal to VI squared, which is 0. So 0 squared is just 0, so I'm not going to write it down. Just 2a change in y, right? So VF squared, we still don't know what that is because that's the thing we're looking for, is equal to 2 times our 9.8 acceleration and our 3 meters. So now this is just going to be 6 times 9.8, which ends up becoming 58.8. Now, as you can see, I just switched these to positives. They technically should both be negative, but if 9.8 and 3 were negative, 2 negatives equals a positive, right? Times the 2, which is also positive, so we would get 58.8. If you were ever to come into a situation where you're taking like a square root and that 58.8 was negative, you did something wrong. Something went wrong because you're not supposed to take the square root of a negative. Now, this is how we get our V of F, which is just equal to the square root of 58.8, which is 7.67 meters a second. And that is the velocity it is going down, so right before it hits the ground. Now, technically, because it's going down, if we wanted to, we could just say it's negative to signal that it is going downward instead of up, or you could just say that that's the velocity, going down, and then you don't need to add the negative right there, right? But that is how we find the final velocity, and like I said, that's the velocity right before it hits the ground. Let's do an actual example now. Okay guys, so a baseball player throws a ball vertically upward at an initial velocity of 15 meters a second. So our initial velocity is 15 meters a second. Just write it down as you read through the problem. Calculate the maximum y displacement that the ball will reach. So we want to know the change in y. Now, ignore maximum. Actually, don't. That signals something. Think about this. When you throw a ball vertically upward at an initial velocity of anything, right? When you throw something, there's a velocity, right? Look, if I throw this pen, it eventually comes down. So I threw it, and the most speed was when I initially threw it, and it gets slower because gravity is pulling it down until it eventually hits the maximum height or maximum y displacement, where our final velocity, because we're trying to calculate this maximum displacement, the final velocity is here when it stops. Because when it stops, then it's going to start turning around and come down again. So that's the maximum y displacement. When it stops, what is the final velocity? It's 0. It's 0. Do you guys understand that? So now, what do we have? We have acceleration in both velocities. We do not have time, so this is the equation we're going to use. So final velocity squared is just 0. Wow. So it's 0 is equal to vi squared plus 2a change in y. 0 is equal to 15 times 15, which I'm pretty sure is 225, if I'm not mistaken, plus 2 times 9.8, times change in y, my friend. So now we have 19.6 y plus 225 is equal to 0. Now, look, we are running into a little bit of an issue here, because I should have said, right, like I said, sometimes this should have been negative. This 9.8 is negative, right? It's not negative 9.8. And basically what happens here is because we're going up, now this is our final and this is our initial, right? So say this was equal to 4, just for example, and this is equal to 1. It's final minus initial, which 4 minus 1 is equal to a positive number. So when we're throwing up, the y displacement is actually a positive number. But now we're going to get a negative number because the acceleration is negative, but I didn't say it was negative here. So I'm going to fix that real quick. That's why you should just always make it technically correct, so you don't run into weird scenarios like I just did. And then now we add it onto the side. So 19.6y is equal to 225, right? And then we just literally divide by 19.6 to get y, or really it's the change in y, is equal to 11.48 meters. And that's how we find the maximum y displacement that the ball will reach. That is the maximum height it reaches, because when it reaches that height, the final velocity is 0, and then it starts coming back down, and then the velocity becomes negative because it's going down. You hear me? Yes, sir. And all right, so let's do one more problem, and then I feel like you guys understand gravity pretty good. Now watch me whip and nay. Now watch me whip and watch me nay nay. Woo woo, whip and nay. Now watch me whip and watch me nay nay. Watch me whip and nay, whip and dab, dab, dab. All right, guys. So Adventure is on top of a 4-meter building. So let's draw that. Sorry, there's not very much room here because it's a very long problem. And his horse is galloping towards his building. So let's draw a little horsey horse. And this guy is going that way towards the building. Or is it that way on the camera? I don't know. This thing's mirrored. And the adventurer needs to perfectly time. Perfectly time when he should fall off the building so that he lands on top of his horse. So basically what it's saying is when the horse gets to like here, this dude is trying to jump off so he can go on his horse, right? Land on the horse while the horse is galloping at a constant speed of 15 meters a second. So what happens? When the speed is equal to 15 meters a second, that means VI is equal to 15 and VF is equal to 15, which means that there's no change in velocity, which if you are in calculus, then you know that acceleration is 0 because it's not speeding up or slowing down. That's what this constant means. So calculate how far away the horse should be so that the adventurer knows when to fall off the building to land on his horse. So we want to know this change in X right here. So how are we going to find that? Well, my first thinking is let's figure out how long it's going to take for the horse to actually reach the building and how long it's going to take for this guy to freaking jump off the building, right? And let's write our change in Y is equal to 4 right here. Okay, so with the information that we're given, because we have a change in Y, what we're going to do is we're going to find the amount of time it takes for our dude to jump off the building and reach the ground, basically, okay? So we're not really accounting for the height of the horse because it's not given, so it's basically just when he reaches the ground. Now, let's see. This, if we're trying to find time, we do not have, let's just use one of these, no VF or no VT. So we're going to use this equation right here. So change in y is equal to VIT plus 1/2 AT squared. So we're going to use this equation right here because we're talking about the person, right? So this is super easy. We don't know the final velocity of when the person is about to hit the ground, but we know that the adventurer is on top of a building, so his initial velocity falling down is 0, right? So the distance from the ground is 4. His initial velocity right now is 0. 0 times time is just 0. Plus 1/2. The acceleration is negative 9.8 because he's falling. And then t squared. So if you do the math, then we get t is equal to 0.9035 seconds. So let's write that over here. And let's go to our next phase of the problem. So now we know how long it takes, and we need to find that how much distance the horse will travel in that amount of time. So now what we're going to do is we're literally just going to do change of x is equal to the average velocity, because it's 15 times time. It's literally just 15 times 0.9035, and that is equal to 13.553 meters. So change in x is equal to 13.553 meters. And that's it. That's our change in x. That's how far the horse needs to be away. And that's it for this video.